So there's an algorithm you follow to get ready for bed, right? You follow an algorithm. You have some, it's kind of like a pattern, right? So there's a set series of tasks you have to kind of run. So if somebody said the word algorithm to me, the first thing I would think of is a computer program. So it's got to follow a certain prescribed set of steps to accomplish something. That's what an algorithm really is. So we're going to finish up section 4.1. We're going to talk about estimation. And I think I warned you guys, there's a lot of definitions, so we'll see how that works. And then we're going to get into developing the algorithms for adding, subtracting, multiplying, dividing. So all the shortcut, all the algorithms we use, like carrying the one and all this kind of stuff, we've already discussed this. That's not obvious. It's not automatic. You kind of want to build it up for a student to show them where things are coming from. And again, that's where some parents get confused when they see these worksheets that are all about building towards something instead of just, here's how to do it, just do this shit, it's just trying to build a student towards something, which can be very confusing to somebody who's just like, just carry the damn one, right? So they're, well, we gotta get there, we gotta show why it makes sense. All right, so if there's no questions on homework or anything, was it the other day my phone fell over and I was like, well, that's the end of class. Everybody leave. All right. So, let me ask you guys this, if there's no questions about anything. When I say estimation, what do you guys think of? Anybody have any thoughts come to mind? Sure, rough answer. I love it. That's kind of like a description of what estimation is. Do you guys have methods to estimate already? Like my one favorite place to go to, because most of us, as we grow up, we normally work in some capacity in food services, right? Sometimes we're waiters and waitresses, sometimes we're cooks, sometimes whatever, dishwashers, right? So I definitely did my time in some various fast food restaurant establishments. We'd work till 2, we'd eat all the chicken nuggets that were left over, and then we'd go get Krispy Kreme donuts. I'm like, that was not the best idea, but that's what you do. So let me ask you this. If I had to estimate something like 96 times 211, I want to estimate that. Does anyone have a suggestion on what you could do to estimate that? Yeah.
You kind of break it down into smaller problems, and then that's easier to multiply. So 90 and 200.
All right. So beautiful. I love this. It's almost like a place you think. So one suggestion would be sort of, and does everybody see, if you do this, will your answer be bigger or smaller or about the same as the real answer? Does everybody see that? That's definitely going to be smaller, right? Which there's not a damn thing wrong with that. It's a nice, you basically just sort of round it both down, correct? So normally, this is also going to be something we discuss. So this is interesting. I'm going to do a few just general things, and then I'm going to start getting a bullet point of all the ideas. But one more idea that's going to come up is rounding. So normally, if I just say round, if I say round 96, 100, you could say to what, Jeff? So if I say round to the ones, 96 is rounded already. If I said round to the tens place, 100. You guys all with me? It's pretty cool. All right, I like it. If I said round 96 down, I am forcing you to round it to the next round number below it, correct? So that would be 90. So this, and what is this? What's the easy way to do this? 18 and then 3 zeros. So that is not the right answer. It should be close, but it's definitely a low-end estimate, right? Can somebody tell me how to get the high-end estimate doing something very similar to what was done? What's the way to get a high-end estimate?
Round the next place.
Yeah, so at around 96 to 100. And then I can round 211 to...
Like 220 or...
You could do 220, you could go crazy and do 300, right? either way. So let's do 300 just to go crazy. What would this be? Yeah, 3 and then 1, 2, 3, 4. 30,000. And that's definitely a high estimate. Okay, maybe. Do you see we had a little bit of a choice to make? I could round it up just a little bit, or I could just go crazy and round it to the hundreds, right? Do you see how, let me see if you guys are cool with this. This would be what's called a front end. Sure, Jeff. I'm trying to weasel in some of these words. Front end, so far, does that make sense? Front end. Weren't we really focused on the first numbers? Front end, okay, here's where things get weird. One column estimates is what we just did. What do I mean by that? I only cared about, well, and this one sort of, I only cared about the first element. I'm sort of trying to weasel this in, but it's going to work out. So if I said front end 2 column, that would have been like Ryan said, make it 100 times 220. Because then I would take into account the second place. You guys sort of with me? We'll do some more examples specifically. I'm just trying to throw some words in here as we do stuff naturally. We'll come back to the front end stuff in a minute. Okay. So pretty cool with just this. Help me out. What is 96 times 211? Who's got that? I don't know if they do. I wouldn't do that. Calculator grafting in my hand.
20,256.
So this is actually equal to 20,256. Okay. So exactly what we thought. We knew this is a low estimate. We knew this was way high of an estimate. So there it is. Cool. I like it. So for example, if you wanted to plan out some huge event, concert or something, wouldn't you normally go for a high estimate in terms of how many people are going to come? Because otherwise you're going to have bad PR because people are going to be like, well, they ran out of stuff halfway through with the shit, right? So you're going to want to have more. And hopefully you have something where you have a program so you can take the stuff to like places to feed people that don't have food, all the leftovers, right? But you want to go over. So there are places in real life where you really don't care too much about the actual number. You just want to make sure that the thing you do is higher than it would probably be. Does that make sense? Okay, I like it. Now, does anyone know how to kind of improve this? And the book actually doesn't even go here, which makes me cry a little bit. But let me see if you guys are cool with this. Let's look at a concrete example of what I'm about to say. Here, this is crazy. What is 8 times 10? 80, 11. Cool. If I make 8 go down to 4, if I take this down to 4, what must I do to 10 to make the result still 80? Yeah, I've got to double it. So basically, it's sort of like a weird compensation. You guys see that? This isn't a great application of compensation because it didn't really make it easier, but it is the idea. I took a factor of 1 and put it on the other one. Are you guys sort of with me? So to improve on this kind of like, this is actually called a range estimate. Does that make sense? Because when I do the low and the high, I get a range for what the actual value is going to be. So if I kind of follow what I just said over there, if I round 96 up, I better round 211 down, right? So if I make them both kind of nice whole numbers, that'll be 220,000, which is the closest we got to the actual answer. Does that make sense? And of course it makes sense, right? Instead of just forcing both down or both up, I kind of like do this, then the multiplication should come out closer. Okay, maybe. I could do something very similar when I add, right? 7 plus 3 is 10. If I make this 5, I better make this 5. So I have to, if I make one go down, the other one's got to go up. Everybody with me? A little bit, okay. All right. Not too bad yet. Oh, where did I put you guys? Oh, you're in here. Okay, I like it. All right, so let me come back to, I just want to start off with a thing to see what you guys would say, to see where everybody kind of was with the idea of estimation. So I'm going to come back and do a few more examples of some specific forms of estimation. Let's see. Boom, boom. Yeah, okay. Yeah, so let's do this. Okay, so there's something called, when I'm doing estimation, we got something called front-end estimating. So let's do some addition first off. So it doesn't really matter what the numbers are. 514 plus 763. So we're going to do a range estimate first. So we basically just did range estimate with multiplication. Now let's do it with addition. You see, yeah, good. Okay. So can you guys take a second to figure out what the low? All right, let me do this very specifically. Yeah, let's just this one. I got to figure out when to kind of throw things in there. Come up with the low estimate for this. So if they just say find a range estimate, that's normally make the numbers as round as possible. They're not being very specific. You just make the numbers really round. So what would the low be? What would I make these?
500 and 700.
Yeah. So 1,200. And what would the high be?
515
No, come on. Make it round, 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 round. Crazy round.
600.
600 plus 800, right? Now, who can see an immediate way to improve on the range estimate? If I get the high and the low, what's one more step I could take? Can somebody give me a guess based on what we've done so far? What the answer is?
Probably somewhere around 1300.
Yeah, okay, so if I average these two, won't that be even closer to the answer? Because the answer is somewhere between these. If I average them, that has a good chance of being kind of close. Now, it kind of depends on how close or far these are away from their rounded forms. But averaging those two very often will actually make the estimate better. Okay, so that's not too bad, right? So the range estimate, if I ever ask you to find a range estimate for addition or multiplication, you just make every part of it, you force everything down to the next roundest number, and then you force everything up to the next roundest number. And that'll be your range, 11. So let's get a little more specific. What about something called front-end estimation? All this gets a little, they get very detailed, which I'm not going to worry too much about the details. What I want you to kind of glean from this is all the different ways you could possibly estimate something. Okay. So if I do this example is going to be a little silly, so let me be more specific here. How did I break it down? Yeah. This is all front-end estimation. This is front-end estimation. Let's do one column. This is one column front-end estimation. So if I do the same problem, what's kind of silly about one column estimation is I don't round in, I just slice the things off. It ends up becoming the low-end estimate. So if I just look at the front numbers, this would be 500 plus 700. That's 1,200. That's crazy, right? Okay. I like it. So one column just means you're literally just, in this case, worried about the hundreds place. the first column of numbers, right? So if you lined all these up, there's 3 columns, hundreds, tens, ones. You're worried about the first column. So if I had a bunch of thousands, the one column approach would just look at the thousands place. Okay. Very inefficient, right? If I make a full range, that's better. This basically will almost always give you just the low estimate. So incredibly enough, the next kind of thing we can do is called 2-column estimation. So if I do the same thing, 514 plus 763, you just chop it off at the second, at the tens place, right? So this would become 510, this would become 760, so then you get 1270. Is that all right? So it's a slightly improved lower estimate. It's definitely better because it's taking more of the numbers into account. It's still a low estimate because no matter what, I force them down. Let me stop for a minute. Okay. Now, do you notice, so there's a couple things here. I could have made this problem so that the last two, in this case, it's almost silly not to just go ahead and put a 7 here, right? Just get the exact answer, correct? But can you imagine making some problems before you've discussed carrying the 1 or anything, and then doing this kind of estimation so that you don't have to worry about carrying the 1 yet? It's just to get a kind of a feel for what this number is going to be, even before you know how to freaking carry the 1 and such. Are you guys semi with me? So again, these can be strung along in a pattern to kind of build a student's understanding up to our everyday algorithms, right? Carrying the 1 and blah, blah, blah. Okay. Let's see. Oh, and then we got this. Okay. So then we have this thing, front end with adjustment. Now it sounds like we're taking a car in to get something done. So here's what this means. So you would do, if I had, for example, sure, we'll do 514 plus 763. So if you do front end 1 column, it would be 500 plus 700, right? And then you do 14 and 63 is like 70. You kind of estimate what those come out to be. So then I get 1270. So the adjustment is just saying, okay, start with just the first 2 numbers and then give it a real quick, rough estimate of what the other digits add up to be. And the idea there is it's easier in this case to consider what 2 2-digit numbers add up to be roughly versus 2 3-digit numbers add up to be, right? I don't know how you guys feel about this. Personally, these all overlap so much, right? You can see front end 1 column is basically low estimate. This is basically the same as what we just did there, right? So they kind of overlap quite a bit. Okay, all right. So I'm not going to be I'm not going to ask you questions that are basically definition questions. Does that make sense? Okay. Blah, 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 blah. Okay. So that's not too bad. The titles of the processes are disgusting. It's almost as if a group of lawyers got together and said, what are we going to call this stuff? We want people to not understand. Okay. So let me ask you this. What really confuses me is over the years, the number of students who don't really know how to round correctly has just gone up. So I'm not sure exactly what to attribute that to, but I think a lot of it, and again, I'm not really aware of this, but I'm aware of it to a certain degree, where in high school, I think they're using calculators more and more and more. Because I know I've gone to a few conferences where they said, why do we want students to memorize facts when we have calculators? I'm like, oh my God, no, what are you doing? And this is why when I say 8 times 7 and a student reaches for the calculator and say, no, 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 and they're like, what do you mean? Like, how do I know what 8 times 7 is? If I don't, I'm like, oh. Sorry. Does everybody in here understand? If I just said round this number to the thousands place, what would that be? What would that be? What number's in the thousands place? 8, right? And what number's next to it? So then I leave it as 8. Now, sometimes I get a student actually do this. And I'm like, the answer you get is supposed to be close to the original number, right? So of course you have to put, okay, so 8,073 is closer to 8,000 than it is to 9,000, correct? Okay, I like it. So if it would have instead have been 598,673, what would the rounding to the thousands be? Yeah, 599,000. Okay, good. And I know a lot of you guys are like, yeah, this is simple stuff, but I just want to make sure everyone's on the same page. So basically, if the next number is anything from what to what, from what's going to make me round it up if the next number is 5 or more, right? So you can kind of, the funny thing is, real quick side note. So let's look at like 875, right? 875. It is equidistant between 870 and 880, correct? And the fundamental idea of rounding is push it in the direction that it's closest to already. So on the surface, you could say, well, 875, why would it go either way? It's right in the middle, right? Which numbers do we round down? Like 870, what would round down to 870? Obviously 870, right? 870, 871, 2, 3, 4. So 5 things we would round down, correct? And if we choose to use 5 to go up, then we would round 875, 6, 7, 8, 5, 6, 7, 8, 9. We'd round that up, correct? Okay. All right, maybe. So, I mean, it's sort of like we decided that this guy should get rounded up instead of down. Another little thing that happens with rounding, I'll see this often, normally with decimals, but not to bring decimals in too early. So if I said round this, wait, let me do this, yeah. Sure. Round this to the thousands place. Somebody will do this. They'll say, well, that would go up to 500, and then that would make that go up to 75,000, so there. You guys see the mistake that was made? Right? And I call this like dominoes. They think that it starts falling from way back here, and that affects, no. So 4,459 is closer to 4,000 than it is to 5,000. Right? The next immediate number is 4, so that should stay at 74,000. Okay, I like it. Okay, maybe. Okay, all right. But as we saw earlier, there's the idea of rounding up and rounding down, which is exactly what it sounds like. It just, no matter what you do it. So if I wanted to round 461, if I wanted to round that up to the next round number. Not the next, just the next round number. Next round number. 470. Is that cool? Yeah, okay. So I can round that up to 470. Now, this is the idea of rounding up. There are situations like when I want to find a low end and a high end estimate, I'm going to round up, round down, no matter what, correct? Everybody with me? So that's not really just if I say round, that means you look at the number. If it's a 5, I go up. If it's a 4, I go down. If I say round up, you're like, push that sucker up, right? So that's a separate idea from the general idea of rounding. So pretty cool that. What I see mostly when I'm teaching something that requires somebody to round is I'll see somebody, if I said round to the hundreds place, I'll just see somebody kind of cut this off. Right, and that's more like truncation, right? It's just chopping something off. It's not really rounding. And I'm not sure what's going on, why that's happening. I'm not sure why people aren't getting as much practice with rounding anymore. So there's not much to this. So if I said round 509, round it down, I would round it down to 500. That wouldn't make it 510. Nothing major there. Okay. Then there's a few really kind of strange ideas with rounding. So we got our traditional rounding, we got our forcing us to round it up or forcing us to round it down, and then you have a couple of really nifty ones. There's something known as round to the nearest even. So if I was doing, let's say, 631 plus 348, and the problem I have to say this, so I'm going to do 2-column estimation. Right? So basically, in this case, it means to go to the tens place. What's the closest even tens place to 631? So it's either going to be 620 or 640, correct? So which one is it? So really when I'm saying even, I mean this guy's got to be an even number. So I can either make it 620 or 640. So which one would I do? 640. It's closer to 40 than 20. Same thing here. So I want to keep this number, I want to make this number even. It's already even, so I'm just going to make it 340. So my estimate by doing round to the nearest even would be 980. And the idea there is, very often in a large string of things to add, what's going to normally happen is you're going to get a mixture of some going up and some going down, so they're sort of average back out. But again, this one, I don't think anybody in here has ever seen this. Have you guys ever seen round to the nearest even? No. There are very specific applications where you would do this, but it's not like a normal thing to do. Okay. Then you've got round to the nearest compatible number. I spelled compatible right, I'm not sure. Anyone remember what the hell compatible numbers were? Anybody, or even just take a guess what a compatible number might be. Could be. So there's a wide range of things that would be compatible numbers. So, for example, if I had 57 times 98, what number is compatible with multiplication? What number is one of those close to that would make multiplication easy? 100, right? So I can make this approximately 57 times 100, so 5700. Is it going to be too high or too low? Too high, 11. Kick ass. So these are all rounding, but they're all using slightly different rules. So when I just say round, we have built-in rules for that. That's the 4 goes down, the 5 goes up rule, right? If I just say round. If I want to be more specific, I've got to actually say round to the nearest compatible number, round to the nearest even, round up, round down, whatever the specific situation is. Okay. But if I just say round this number, it's your normal standard 5 goes up, 4 goes down, right? Oh yeah. So, real quick, it's really kind of funny to me. I told you guys this before. I've never taught elementary school, so I continuously feel a little bit like a wannabe in this class. But it's kind of surprising to me this book didn't talk about what I consider to be real estimation. Which again, if I wanted to do what do you got, Jeff? 8.7 times 112. So we talked about this a second ago. How could you kind of make that work? What would you round things to be? Sure, you could make this 9, which means you have to make this. If I go up a little bit on this one, I have to go, so maybe 110, because I didn't really go up that far, you guys with me? So that would be 990. I was thinking I would do 10 and 100, and that would be 1,000. See how close those are? So if I make one go up and one go down, then overall I should average out. Okay, I like it. So let me push this a little bit. Let me see what you guys think. And by the way, what is 8.7 times 112? Has anybody got the calculator out? I don't feel like doing that in my head. 974, I love it, okay. So these are both a little over, but not that much over, so it's pretty good. What about this? What if I had, what do you got, Jeff? You can do it, there you go, buddy. Right stuff, there it is. 2811 divided by, you can do it, man, 739. All right, now I'm dividing, correct? So real quick, just to kind of get you in the right mindset. What is 20 divided by 2? 10. That's crazy. If I make 20 become 40, what do I divide 40 by to still make it 10? 4. So both have to go the same direction. That should kind of make sense. Division is sort of the opposite of multiplication. So if multiplying requires me to, if I move one down, I got to move the other one up. Division, they actually have to go the same way, because they're sort of opposites of each other. So does anyone see the numbers would work beautifully if I just go a certain direction? I could go up or down, either way. So what do I want to do here? Besides pretend like that problem doesn't exist. You can take it both down, because if I do 2800 divided by 700, see the zeros cancel, yes? And then 7 into 28 is? 4? And again, real quick, help me out, computer, calculator people. What is 2811 divided by 739? I think that's too high. We'll see if I'm right. I think it's 3 point, let me make something up, 3.81. Holy shit, that's pretty good. So it's actually 3.8, blah, 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 blah. Okay. And 4 is pretty damn good, especially for government work when the actual answer is 3.8. Okay. I like it. Now if it was the price of gasoline, number one, that'd be great nowadays, but 20 cents would be huge. But still, it depends on how precise the answer has to be, will tell you if you should even be freaking estimating in the first place. Somebody with me? Okay. So true estimation tries to average out the changes you're making. You don't just wholesale change everything one way or the other. You try to make sure that things are going the right way. Okay. I want to ask you guys, I think I brought like a thing of calculators before. I don't necessarily need you to have a calculator right now, because I'm going to show you a few things on the overhead, but what kind of calculator, who in here has their own TI? Anybody have their own graphing calculator? So you got a TI scientific calculator, right? Okay, so I should be more specific, I'm sorry. Who has their own graphing calculator? Okay, a few, yes, okay. And the rest of you, do you have like a scientific calculator? And when I say scientific, I mean it's got a silly amount of functions. Let me show you. So I'll show you a couple, the difference between the two. We'll talk about a few buttons on here real quick. And again, you know, what's funny is, I'm talking about calculators, and I'm hoping that most of you guys don't use calculators at all in your classrooms. But this is for your own edification. Okay, just want to point out a couple of features. Okay, so you got this kind of calculator, right? So hopefully everybody has something that's a little more than just the little tiny one with the plus, minus, divided by, times thing, right? Even if you have, what's funny to me, real quick, if you ever use your calculator in your phone, it's interesting to me the number of people that don't realize if you just turn it sideways, you get a lot more functionality, right? So that's happened to me almost every class. Somebody's on the phone, I'm like, just turn it this way. Holy shit, you get square roots and all this kind of stuff. So this little dude is a step up from the normal 4-function calculator, because I'm certain you guys are aware of this. If I plug stuff in, it actually shows me everything happening, right? So the old calculators, you would put 7 minus 8, and the 7 would go away. So then you'd have, you're like, what did I put 7? Or that might just be me, but the interesting thing is, the old calculators where the number disappears, they don't normally understand order of operations. They just do it as you give it. So if I wanted to do 7 minus 8 times 2, what would I have to do first? 8 times 2. Multiplication comes before subtraction, right? But if you have an old-time calculator where you do 7 minus 8 times, it would be -1 times 2 is a -2. And that unfortunately leads to a lot of confusion about order operations for students, because maybe the teacher doesn't catch, they still have one of those old calculators that does not understand order of operations, and that really gets confusing, right? Okay. Does anyone know on this calculator where the exponent button is? As I say that, I'm like, it's been a while since I used this calculator. There it is. This calculator looks the same as the TI calculator, but so it's this little caret dude. So on the TI, you got a little caret dude, right? A little caret. So I call that the to the button. So if you wanted to do 5, oh, get out of there. 5 to the 3rd power, you get the 125. Sorry, as a math teacher, it's interesting to live near the 8 and the 125, perfect cubes, blah, blah, blah. Okay. All right. So some of you guys, does anyone have a exponent button that looks different on the calculator? Anybody have a different button? What does yours look like?
It's like an X with the little blank thing in the top right corner.
A little blank dude? Let me see.
And a
I'm
little
curious.
It's like a
shaded in.
dotted square.
Oh, you got one of those? You got a funky dude.
Yeah.
Oh, this year.
Yeah.
Oh, is this X to the N maybe?
No, like you could just plug in 6.
To the-
And then it goes up to
Ooh.
4.
Oh, it's a little
Six.
box dude.
Yeah.
Okay, okay. All right, that's the first time I ever saw that. So it's an X to a little box, which is nifty. So it's sort of like a blank space. So
So it kind of just looks actually like exponent.
11. Because then on the screen, it's actually, so if you hit six, can I borrow yours? Sorry, thanks. Thanks. All right. Look at me, all right, I gotta tell you guys, as if you didn't think I was weird enough already, when the tax man would come to my parents' house, I would ask if I could play with the calculator. And you're like, what's Jeff gonna do? All right, so if I do, so here's the little button. Let me zoom in a lot and see if I can see what the hell it is. Yeah, look at that. All right, so there's the X, and it's got X to the box. I love it. Which is kind of nifty. It's like a blank space idea. So if I do 7, and then do 2 that on the screen, is kind of nice. It's got a little thing, and then I say, okay, let's do 8. Let's see what it does. Yeah. All right, cool. Anybody else have something different than that? Or anybody not even sure where their exponent button is? Does anybody have like a X to the Y or Y to the X? There we go. Okay, good. That's the standard one on a lot of scientific calculators, is it just says X to the Y. So you hit the button that's going to be the base, you hit that button, and then you hit the number you want for the exponent. Kick ass. Oh, I had a couple of things I wanted to point out. Blah, blah, blah. Oh. So the fact that you can put an entire line of computation in here at once, all of a sudden means your calculator has to have parenthesis buttons. Now what's interesting is if you look at a TI, do you see how there's a comma? It's got some more punctuation. Okay. So in here, if I wanted to do, if I really wanted to do 7 minus 8 and then divide and then multiply by 9, I'd have to tell it parentheses 7 minus 8 and then times 9. Yeah, you have to put an 8 there, Jeff. There you go, buddy. Okay. And what's really nice, of course, is that ability to go back and edit. You can do both on the scientific calculator and the TI calculator. You can go back and edit, which is really useful. You have a class like my stats class, our formulas get really big. So if you look and you made a mistake here, like, oh shit, well, you can just go back and edit it, thank the gods, right? Okay. All right, and then there's a little thing about scientific notation. If you guys have a calculator, let me see what your calculator does with this. Everybody who has a calculator out, do this with me. We're gonna do 8,888 to the 5th power. I'm really curious what you guys did. So do 8888 to the 5th. Now mine does this nifty thing, which is really kind of cool. It actually just says times 10 to the 19th. Now obviously, the answer to 888 to the 5th power is not 5.5. I love it when a student writes that and just circles in. I'm like, just step back from the problem for a second. That can't be the answer, right? This one's kind of nice because it says times 10 to the 19th. Does everybody understand what that means? What would that mean? Times 10 to the 19th. You have to move the decimal 19 places that way. So, of course, 8888 to the 5th power should be stupid big. And that's pretty much what I see here. Anybody else have a different thing showing up than that? On my graphing calculator, it would look like this. Oops, not times. Not 3/8. Has a little e dude, right? So it's 5.5 e 19. And little e dude just means times 10 to the. So it just kind of hides what's going on. This is nice because it actually shows you, oh yeah, it's times 10 to the. All right. I'm going to let whatever happens in your calculators be there because nobody's telling me if anything weird happened, anything different happened. No? Okay. I'll stop playing with calculators. All right. Throughout this semester, we're not going to use the calculators too much, obviously, because most of us really shouldn't be teaching much of anything on the calculator, but it will come up every now and again. So if you have any issues with the calculator, just let me know. So that was a little side note. Okay. So that is the estimation section, section 4.1. Oh shoot. This is what I came in here early for. We're about to get into section 4.2, which is where we develop some algorithms for doing stuff. Unfortunately, there's just not enough of these to do everything I need to do with you guys. And this would just be so cool. A kid would love the shit out of this thing. Throw a few things over here. Okay. So, what I want to do is, since you all can't get your own, you all can certainly draw picture representations of flats and longs and units and so forth. Bless you. So just to give you an idea, and then I'll actually do it with the real stuff. There we go. Can you guys represent, here we go, this problem, drawing flats and longs and so forth. So again, you don't have to mark off on the flat 10 to 100. No, God, no. You just have to make a square, right? I just turned you off, didn't I? Alright, so for example, if I wanted to do 433 plus 122. I like it. Okay. What would 433 look like, of course? What would it look like using flats and longs and so forth? So we have units, which of course is the ones place. I'm going to represent that with a dot. We have longs, which of course represents the tens place. Then we have flats. They're basically 10 times 10, so that's 100. They represent the hundreds place. It's crazy. We won't put up the cubes today, thankfully. So if I want to do 433, so I'm going to do this as a square, a line, and a dot, right? So it's like the next level up from line stuff. 433 would be 4 flats, 3 longs, and then 3 units. Right? And then 122 would be 1 flat, 2 longs, 2 units. So just to show you, with this stuff here, I'm going to give you a few problems to try on your paper. And maybe I'll see if anybody feels confident enough to come up and do it up here in front of everybody. Let's see. Let me just do this one. Oh boy. Okay, I got more of this. Okay. I think I have more. Yeah. Alright, so then I got. Let's see. It's gonna be exciting. Alright. So I'm gonna do this. 1, 2, 3, 4. I got 400. Man, this is crazy. Just to make it there. Alright, that's better. 400. 1, 2, 3, 30. Okay, out there. 1, 2, 3. That's better. 30. And unfortunately, color scheme goes away. 30. So you can imagine just giving a student these things, and at this level, they're gone a little bit. Obviously, when you get to these, you're gone a little bit beyond just counting each one, because that would take forever, even though they would actually have no problem with that, because they want to show off that they can count. 433, and then 122. All right. And of course, this would just be a matter of putting these together. Now, this problem does not involve any carrying yet, correct? But you know I'm about to go there. So then I do this, so that would make 555. And again, this is so beautiful because you could actually have them count, and at this point they would understand they don't have to count each thing, they just say 100, 200, and so forth, right? Okay. If I wanted to create a problem that involved carrying a 1 or something, right? So for example, can you guys please just draw me the picture of this problem? 100 and, let's just do this, 179 plus 118. And I'll catch up to you. Yeah, okay. No idea if that's catching. So 179 would be 1 flat, 7 longs, and then 9 ones. 118 would be 1 flat, 1 long, and 8 ones. So then what do you think you'd have a student do if they try to add these together? Can you represent that on the paper? What would happen? Okay, sure. What's funny is, it's kinda nice, cause the algorithms we're gonna build are gonna start going, this way, and then we sort of start to develop the idea of carrying stuff. So, in the hundreds place I have 200, right? In the tens place I have 80. In the ones place I have 17, right? And again, you can see a student counting and saying 17. Do you see how this is starting to approach the idea of carrying a one? Now, real quick, I have put down here, and you guys can see how to explain to a student that the one from this place actually leaks over into the tens place. Then you can sort of move in the direction of carrying a one, correct? Visually though, kinesthetically, what could you do here to actually emulate the idea of carrying a one? Yes?
Take one of the ones from like the 7 and put it over to the 9 ones from the 179.
Oh, I see. So take one of the ones from here.
Or yeah, from the 80 that you have, and then move it over to the 9.
And so this makes
Another long.
a long. And the funny thing is, the long looks like a one, so carrying your long, which is a one. I like exactly. Which again, I get a little excited about this because it's such a beautiful toys that are translating into mathematics. And the more you have a student mess with the toys, they're going to understand better the foundation of what carrying a one means. Now I have a visual in my head. Carrying a one just means getting 10 of these together and making it into this, so then it actually goes into its right place. It comes over to the next place. Okay. And again, I'm kind of staying here for a minute because the idea of carrying a one or borrowing when we get to subtraction is not immediately obvious, right? Okay. So what would happen here? Let me come back to a specific place I want to go. Oh yeah. Yeah. What about 49 plus 63? Take a minute, just try to do the whole thing just with pictures, just with the flats and longs and so forth. This one's a little more involved, right? Not like difficult, but it's definitely different. So 49, no, Jeff. 40, 2, 3, 4, 5, 6, 7, 8, 9. And then 63. A lot of things. So the funny thing is, if you do it visually like this, it almost doesn't matter which way you come at it, because you're just reorganizing the pieces. When we have the algorithm the final standard algorithm, you go from right to left, correct? And that's the only way that specific algorithm will work. So help me out. What did somebody do to get started on this? Yeah, so visually you can see 4 and 6 pieces makes 10, which makes a flat. And again, on one level, you don't necessarily, especially when you're very first starting out with this stuff, you don't have to call that 100, just a flat, right? And so they can get used to the visual and get used to just what's happening just physically with these pieces. So that's there. So it seems like there's an empty space here, but of course, what happens over here So I can do like I did before, I can sort of group these. So that makes a flat, and then of course these, and then of course I get what number? Holy shit, right, okay, I like it. Okay. So let me show you this in a couple different ways. So you have a very tactile way you can do these problems. In fact, let me do it here. Let's right, set this up. So you got, so, and again, you've seen one, I'm gonna show you some videos here in a minute, but you've seen some of these videos already where you've got 4, so if you put this together, it actually does create that shape exactly, right? So they can get that idea without a connection to the number necessarily, they can just get that idea visually. Then I've got these, when I put, and yes, I'm gonna do this, give me a second. When I put those together, you can do it, Jeff. Oh, this is so exciting. What'd you do today? Watch my teacher mess around with little yellow squares. There we go. So there you go. Get out of here. And then of course you get the 1/12. I'm sorry, I don't know if you can see some of that, but it's basically what we do on the paper, okay? And again, I certainly am guilty of not infusing some of my lessons with enough kind of hands-on stuff, but some of the classes I teach, it's not the easiest thing in the world to do, but you guys are gonna have a much easier time with that, because that's basically where you want almost everything to start, depending on what age you end up teaching. Okay. So so let me show you a couple different representations of some of these. So looking back at 49 plus 63. How could you do that? Okay. I see, you're just crazy. So we got our flats and longs and so forth. We've been already focusing on that. There's a little weird thing called a chip abacus. Now, has everybody ever heard of an abacus? Maybe I could look up a video later, but it's basically where you flip the beads around and so forth. I have something called a Himalayan calendar, which is basically beads you put in places, and some of them represent the day, and some of them represent the year, and some of them represent the month and so forth, right? Which is not like an abacus for real, but when you're doing all this flipping back and forth, and somebody says 78, so they did the work, they did the math. Have you guys ever heard of a slide rule? Some of you guys are like, what? I had a circular slide rule, which was really cool, and I lost it, I'm sad. Anyway, so these are all, before calculators existed, these are just actual things we could hold and turn and do stuff with that I could actually do calculations on. More than you might think, right? Okay. So the way this would look, just in case, I can't remember if I assigned any problems like this. So here's what this is. Oh yeah, that's right, I do need that. So what that would do here is, I've denoted the places, so I would put 4 chips here, and then 9 chips there. So that's 49, crazy. And then I'll put 6 chips there, and then 3, and that's 63, crazy. Now, real quick, you can start to see these are visually distinct. I know exactly what place I'm in when I just see the shape, correct? This is sort of an intermediate step where we go, okay, it's gotta be less dependent on the shape of the thing, and it's gotta become more dependent on the place I'm in. You guys with me? Because when I just look at the number 4,783, there's no shapes there. I have to understand the places. But what would the work look like here? It would actually feel exactly the same as what we did earlier. These all together make 100, correct? So this would go, let me put the answer down here. These would go there. And then of course I could do the same thing we did earlier where these make a 10, and then I got the 2 left over there. So the funny thing is, you can all see the idea is the same. But this feels very different. For one thing, it's not got any connection to shapes. It's just places. right? And I say this a lot, but so much of what we consider to be obvious is so desperately not obvious, right? Okay, so this is kind of an intermediate step. And then you've got this thing, let me see, what they call it, oh yeah, this is just place values. So it starts off the same kind of way, except now I'm gonna use numbers. So I got my, I used a different problem over there, that's why it's tripping me up. 4963. So then when I add these together, see if you guys are cool with this. I get 12 and 10. And now you can really start to see where we're getting away from, now I'm not done obviously, please do guys, right? The answer is not 1012. Do you guys see how this is similar to a student making a mistake when they're changing to like base 13 and they put a 12? So it's really two places instead of one. So right now that's basically where we are. We have two digits in a single place. So these, of course, this one bleeds over into there, right? This one bleeds over into there, and of course the 2 is still there. Maybe. Let me see. Yeah, let me go there. Yeah, perfect. And this kind of, okay, is everybody semi-decent with that? So you can see the progression. You got something you can hold, shapes tell me what it is. Then I've got places with the same shapes, but they each denote a different amount based on the place they're in. And then of course I've got just numbers. This still isn't great because I am sort of representing 2 digits in one place, which is bad. But it's sort of like as the next step would be talking about carrying stuff. All right, so watch this. Yeah, let me come to it more big. Here we go. So if I do this, so there's something called the intermediate algorithm. Just make it one big letter. There we go. Algorithm number 1. So if I do this 49 plus 63, yeah, I love it. So basically all this does is 9 plus 3 is 12. 40 plus 60 is 100. So then I got 112. That's crazy sauce, right? That's not how we add things, correct? But you can see how it's getting closer. It's definitely closer than this stuff was, correct? Okay, but it still kind of carries over some ideas from that guy. The fact that the 12 kind of bleeds over now is more obvious, more immediately obvious. Okay, I like it. Then, incredibly enough, we got intermediate algorithm 2. This would be better with more. That's true, Jeff. It's too bad. Yeah, I should have done a bigger number, but that's too bad for me. For this small of a number, it's going to be the same thing. So I should have done a bigger number. That's too bad for me. This is where you basically just do that. It's the same thing. I'll do a bigger number because then these two will be different. So standard algorithm, which is the one we actually use, would be 49 plus 63. And this is, of course, where everything kind of happens here instead of below. 9 and 3 is 2. That's crazy. Carry the 1, and then you get 11. So everybody's sort of with me. This is not the most exciting thing in the universe ever. But for your students, this is going to be some serious shit. They're going to be soaking this stuff up. Right? Especially if you make this progression really nice. From the visual, kinesthetic, all the way to the purely algorithmic. Okay, so let's try it real quick. Let's try a bigger number. Sure, 489 plus 372. Okay. So if I do it intermediate algorithm 1 method, I would do 11. 80 plus 70 is 150. 400 plus 300 is 700. Now the funny thing is, this intermediate algorithm 2 is going to look a little bit the same, but there's a slight difference in now I see what I did up here that wasn't quite right. 9 and 2 is 11. 8 and 7 is 15. 4 and 3 is 7.
So you just don't write the zeros.
Pretty much, yeah. But now it's sort of, all right, let me say this. And again, you don't necessarily have to do all these steps, but do you see the importance of actually getting to this step? It's, what's the most important thing for a student to get down about our number system is the places and what they mean. So 8 and 7 is one place over, so if it was 4 and 3, I would just put a 7 here, but it's 8 and 7, so I put a 5, 1, 15. And then this third place over is where 4 and 3 goes. So the place tells me that it's hundreds or tens or ones, correct? Seems like a very subtle, very subtle. Okay, I love it. You guys look appropriately amazed. Okay. And then of course standard algorithm would just be the carrying stuff. Nothing surprising there. Now here's something really cool. I don't think any of you, let me know if you've ever seen this next thing, ever. It's called the lattice method. Does that sound familiar to anybody yet? Okay. Because the first time I ever saw this method was basically when I first taught this class. It's definitely not a method I use all the time. So what you do your 489, 372, and then you do this. You make a little lattice underneath, and the lattice gets very interesting. Okay. Let me zoom in a bit. So everybody with me on that? Now please, I'm honest. I know that as a math teacher, I find a lot more things fascinating in here than you might. But this is actually kind of cool. So go with me. This is kind of cool. Did I put too many? I did. I'm thinking about multiplication. I'm sorry. Later with multiplication, we're going to need more stuff. I didn't need this whole bottom one. Sorry. What's 9 plus 2? 11. See that? You with me? So if I would have had like 7 plus 2, I would have put 09. You guys with me? What's 8 plus 7? 15. And what's 4 plus 3? 07. Now watch this. Add diagonally. So here I have a 1. Here I have a 6. Here I have an 8. You guys see that? 1 plus 5 is 6. 1 plus 7. If I add diagonally, are you guys all with me? Okay. You're all just like, it wasn't as interesting as you said it would be. I'm sorry. Okay, I like it. Has anybody ever seen that method before? Yeah?
Yeah.
Sweet. In high school or something? Or not high school, but like,
It was in elementary school.
yeah? Okay. Did you do it, do you remember if you did it for multiplication also?
Possibly, I remember doing addition.
Alright, okay. It's sort of related to, when you guys were in algebra, did anybody ever do this kind of problem with a box, putting like, yes? So it kind of feels like that to a certain degree, but it's got that one extra little layer of cutting each box in half. Okay, okay. Am I out of paper? No, good. So in a minute, we're going to get to the lattice method for multiplication. So incredibly enough, we're going to talk about subtraction now. Hold on, I really zoomed in. So if I had, for example, 387 minus 211, and I want to do this with the longs and flats and units, you're not going to represent each of these individually. Does that make sense? What method do you think we're going to use? What's the easiest way to do subtraction when I have a certain number of objects and I want to subtract away? Of course I'm going to use take away. So I'm not going to represent, it might just be me that one. I'm not going to represent each number. So I'm going to represent 387, so 387 would be 3 flats, 8 8 longs, and I almost did heel bones and such. Okay. By the way, I forgot to say this. Now that I said the Egyptian thing, if you ever go to which museum is it? Museum of Man? Probably. I don't remember which museum. There's a museum that's got the Egyptian, they have Egyptian tablets and such. If you go there, you'll actually be able to go, oh, that's a number, it's a numeral. I know that shit, right? It's kind of weird. The first time I did that, when I first learned the Egyptian hieroglyphic numbers, and I went to the museum, I was like, it's such a weird thing to go, okay, that was created millions, thousands of years ago, and I can read part of it. It's kind of nice, right? Of course, it might just be me over. So like you guys said, this is a perfect kind of like analog to the work you would have done already with takeaway. So now what do you think I'm gonna do if I just got it drawn like this? What could I do? Yeah, you could cross them out, I like it. So cross out 2 of these, cross out 1 of these, and cross out 1 of those. And you just say, okay, what I got left? 1, I've got 7, and I've got 6. Right? And of course, I mean, you know it's going to look like, but 300, let's see, 80, oh crap. I feel like one of those kids in the videos. 87, is there enough room for everybody? Can you guys see these? So there's 387, I believe. Yes. And then it's so beautiful because you can just, so here, let me make sure there's 300, so I take 2 of these away, and I take 1 of these away, and I take 1 of these, and then they can just count what's left over. It's beautiful. And at this point, they don't necessarily have to have a big connection to anything algorithmic, anything written. Okay, so what does this look like in the other forms that we looked at a second ago? If I do the chip thing, it's going to look very familiar. So I would, this is just too right. That's better. Okay. What was it? Wait. So I got 380. Seven. And of course, here you can just take, like we just did, take 2 of these away, take 1 of these away, take 1 of these away, and then you just count what's left. That is very obviously the exact same thing we just did, but again, that's actually a decently big step in the right direction, let's say right direction, in the direction of the method that we use primarily nowadays. Okay. Oh, how you guys all doing? I mean, I know we're just now talking about subtracting numbers, but we're not just talking about that, we're talking about how to show other small people that have never done it before. So I just want to show you in the book real quick, because you must be getting tired of me trying to draw stuff. Here's an example they do about 423 minus 157. Now, there's something interesting that happens here. Okay, this might not be the right thing I want here yet. Oh yeah, this is a little more, okay. Okay, let's see. I don't know if you got your book with you, but let's kind of look at this. So I've got 423 minus 157. Now, in order to do 423 minus 157, it would require some borrowing, correct? All right, so it kind of makes sense that visually, or with these guys, we're gonna kind of break one of these pieces up, and immediately you see how that relates to borrowing, right? So the funny thing about when you borrow, real quick side note, I know you guys all know how to freaking subtract and borrow shit, but do you ever really consider for a second what you're really doing? And I'm gonna scare some of you guys by putting some fractions down in a minute. So to do this problem, where would I start? just to do it the standard way. Right, yeah, I can't do 3 minus 7, so I've got to borrow, and of course, this represents 20, so I am literally borrowing a full 10, and that's why that becomes 13. And then here I gotta do the same thing, I gotta borrow from this dude, that's 100 I just borrowed, which is 10 tens, so that's why this can become 11. So real quick, I don't know if you guys ever saw, and then of course you get blah blah blah, to 266 I think it is. Have you guys ever seen, I'm gonna throw this at you a little early, but I just want to. You get, real quick, easy question with fractions, I know. I know I'm doing fractions. What's 7 3/4 minus 5 1/4? That is a relatively easy fraction problem, primarily because they already have the same denominator, right? So how do you use 7 3/4 minus 5 1/4? Yeah. So you get 2. Yeah. 2 2/4, which can be 2 1/2. So basically, it's just like what we're doing here, except they didn't have to borrow anything. I do, I've got the hundreds and so forth. So watch this. What if I had 7 and let's do 1/5 minus 5 and 3/5? There's an issue here now, right? It's pretty much exactly the same issue we had here. I was trying to take away more than it had in this lower place. So we're gonna do exactly the same thing we did before. This really highlights what you're doing here. You are literally borrowing exactly 10 from this dude, and this is why it becomes 10 plus 3, 13. Right? So here, has anyone ever done this? Does anyone remember how to do this? Okay, now watch this. Everybody cool with the fact that I can't do 1/5 minus 3/5? Okay. I think I'm gonna show you the other way to do this, but I'll just do that in a minute. So watch this. I can borrow a 1 from the 7. Isn't 1 2 divided by 2, for example? Isn't that 1? 2 divided by 2? Is 3 divided by 3 is 1? So 5 divided by 5 is 1, correct? So if I borrow a 1, I can actually add a 5/5 to this dude. This is exactly the same thing we just did up here. Right? When I borrowed 1 from him, it wasn't really 1, it was 1/10, right? So when I borrow 1 from the 7, it isn't really 1, it's 5/5. So now I can make this 6 6/5 minus 5 3/5. And this really hammers it home. Isn't this overloaded? Which is fine. The same way, this is literally 13 in a single place. That's what that is. That is 13 in the ones place. And we're only allowing it to exist because after I subtract, it's going to be fine. Everything's going to work out. So we're okay for a minute, right? So here, of course, I get 6 minus 5, 1, 6/5 minus 3/5, 2/5. I like it.
3/5. 6 minus 3.
6 minus 3. What did I say? Okay. 1 3/5. All right. If I could read my writing, the awesome. 1 3/5. Okay. Now watch this. This is kind of cool. Just because I'm doing this, I want to show you guys this. I'm going to go one step further. And I understand that I'm doing. Now watch. I'm just going to do 7 minus 5 is 2. And what's 1/5 minus 3/5? Negative 2/5, right? So what's 2, I should have put that there. What's 2 minus 2/5? 1 3/5. Same answer, yeah? So there is kind of a way around. You could do something very similar with whole numbers. But it's normally not done because there's more than 2 places to kind of take care of. Okay, all right. Enough of that, enough, sorry. I just want to go to fractions for just a second. Oh yeah, good. All right, let's talk about multiplication real quick. If you think for a second, if you wanted to represent multiplication with with these guys, right? It would be easy, so for example, if I wanted to do, represent 133 times 2, why would that be easy with this stuff? Here's 133. What would I do to represent 133 times 2? Yeah, so we did basically the same thing before, right? Just put these two, and then I just start putting these together, and then I get my 266, right? Okay, so what if instead I want to use flats and longs and units and such to represent, not that, that's too easy. I want to represent, what do you got, Jeff? 82 times 110, sure. Do I want to do 82? No, not really. Let's make this 32. You'll see why in a minute. The process will still work, I just don't want to draw that much quick. So real quick, by the way, how would I do 10 times 10? Isn't this 10 and this is 10? How do you think there's a way to do 10 times 10? I mean, 10 times 10 would be what shape? The flat, correct? What geometrically do I do? What leads to multiplying two numbers together geometrically? This might be too weird of a question. Like if I wanted to measure how long the wall is, I would just measure it, right? But if I want to know how much carpet to get, wouldn't that involve multiplying two numbers together? So if I want to know 10 times 10, I can sort of look at it as that idea, right? So this would be, for every one of these, there's 10 of these. So that's 10 times 10, that makes 100. So watch this is kind of cool. 32 times 110. I think I'm going to try to do this just drawing, because otherwise I don't think all this is going to fit. You'll see why in a minute. 32 would be along, and then 2 units, correct? Okay. Turn you off, let me see. Okay. And then 110 would be a flat, along, I think I want to put this, yes. And that's it. So, for example, this, what have I done? Okay. This would be, this times this would be a flat. Just like we said a second ago, if I do this times this, I get a flat, correct? Okay, I'll lock it. If I do, let's work on this first. So I'll get a flat there, and a flat there, and a flat there. And then I get, watch what happens here. I basically get, what's one way to look at it? Yeah, I get 2 longs there. That's 1 times a long and 1 times a long. Okay, maybe. This one, I'm gonna get, let me think for a second. Down here, I'm gonna get, let me think. Yeah, this gets a little weird. I should have oriented this the other way, but that's okay. So this is gonna be like a full flat and a full flat, 1 times that. This is gonna be like, yeah, I've gone a little bit more than I wanted to, that's okay. This is gonna be like 10 of these. So this is gonna be cube, okay, so let's see what we get. We get, what are each of these? Yeah, they're each 1,000, right? Because the flats are 100. So this will be 3,000. And then how many hundreds do I have? 500. And then I've got 2 tens, right? And what is 32 times 110? Let's see, 32 times 100 is 3,200. 32 times 10 is 320. So then I get 3,520. Freakadelic. Now let me do a slightly smaller problem. I didn't necessarily want to go to the cubes. That's my mistake. Okay. So if I do, for example, 34 times 12. Try to set this up. So 34, run it along this way, and then 12, run along that way, right? So 34 would be, how many longs? 3. And then 4 units. 12 will be 1 long and 2 units. Okay, now. So basically, what you can think of a long is 10 little units. So for each unit, I'm going to get one of these. So that's why a long times a long makes a flat. It's the idea of area, right? So if I measure one side of a square room and another side, I just need to multiply those together to get the area of the room. So I'm going to get 3 of those. Down here, I just want to repeat this. This means I get 1 of these for each one. So I get 1, 2, 3, 4. And then up here, something very similar happens. Now, what do you think is going to happen here? I mean, each time I do a unit by a unit, that's just a unit, right? So I just kind of repeat this twice. Let me stop for a minute. Now let's gather what this is. What do we get? What's that? 300. What do you get? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 100, right? And of course this would be 8. So I get 408, which thankfully is what 34 times 12 is. Okay. I like it. This is a little bit messier. And of course multiplication should be more difficult, especially when you're doing multiplying by more than just a single digit, right? Multiplying by 2 or 3 is relatively easy. Just repeat it that many times. I don't want to repeat 34 12 times necessarily, right? But that would work. Okay. So just to show you that there is a way to do multiplication visually using these shapes, that's the way to do it. And by the way, I just want to show you the idea that gets to a cube. So if I have one of these times one of these, I'm basically saying for each element here, I'm going to put one of these down. So if I do that, I build a cube, right? Okay, I like it. Okay. Okay. So now let's start talking about, so we did the intermediate algorithm steps for addition. Now let's do the intermediate algorithm steps for multiplication. Did I feel like it, was it just for addition we did? Yes, okay. So this guy, what do you guys think I'm gonna do for the first little baby step of how to do this?
2 times 4.
2 times 4, good.
And 2 times 3.
2 times 30.
Per 30. 10 times 4.
Good, 10 fours,
10 times
10 times 30, I like it. Stop for a minute. And then of course you just gather all that up and thankfully it becomes 408. Now real quick, do you guys remember rewriting this to use distribution? I'm gonna go one more step than that. I can't remember if I showed you, but if I do 30 plus 4 times 10 plus 2, right? You guys remember what to do here? What? I almost don't care if you know the name of it, but you guys know the name of it? What do I have to do here? You guys remember? I love it. Beautiful. This is actually the best silence I've ever heard. I don't want you to know the name of it. It's called foiling, right? And that's another example of something that I wish we never made up. Whenever we make up a mnemonic device, it's sort of like communicating to students, you couldn't do this without this mnemonic device, right? And I kind of don't like that. Has anybody ever heard of SOHCAHTOA? Okay, so unnecessary. Absolute bullshit. Sorry if you enjoy it. There's a lot of camp jokes about it, whatever. Okay. Anyway, if you've never heard of SOHCAHTOA, it's trigonometry, so if you don't need that, you're fine. But if I do this, don't I get 300, right? Plus 60, does anyone look familiar? Right, it's exactly the same numbers we got. So we're basically just doing something akin to distributing the various pieces. Okay. Just to kind of show you that's really what goes into this. Second step, we start to kind of consolidate this a little bit. So what kind of makes sense to do here would be twice 34 is 68. And then 10 times 34 is 340. And then you kind of add that together. And of course the fun ending is this basically our standard algorithm. Again, this is just a 2-digit times a 2-digit. So it's basically our standard algorithm. The one difference would be if I had to carry something, I guess. But I mean, here we would just do 8. 2 times 3 is 6, 1 times 4 is 4, 1 times 3 is 3. Was anybody ever taught to do this and just leave this blank? Yes? No? Okay, some of you guys yes, some of you guys no. I always put 0 there. Doesn't matter. You still get 4 it's me. Okay. So real quick, if I did intermediate algorithm 2 on a problem like, let's do, if I just make it 37 times 12. That would be about the same. Yeah, you're really taking a jump. Because then I would just still double 37. So the carrying wouldn't really matter, but this requires a student to know what double 37 is in their head, right? Double 37 and 3 times blah, 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 blah. Okay, great. Oh, all right. What time we got? You guys are like, that's enough. Okay, one last thing. I promised you guys we'd do lattice multiplication. So let's do 5,132 times 26. So here's how we do this. It's going to feel a little familiar to some of you guys that use that box method. This is what I was thinking about earlier when I put too much stuff down. I don't know why you got such a big box there, 5. So this is sort of nice, nifty. Have you guys, real quick, have you guys ever seen, the Chinese method, I think it's called, where you kind of cross. If you want to do 2 times 3, you just count the number of times these cross, you get 6. You ever seen that? Okay. There you go. Of course, the larger these get, the more complicated it gets, but it actually still works, but it's, Okay, but this is not that, sorry. So what you do here is 2 times 2, 4, 2 times 3, O6, 2 times 1, O2, 2 times 5, 10. 1, 0. 6 times 2, oh, I forgot you, sorry, little dude. 1, 2, 6 times 3, 1, 8, 6 times 1, O6, 6 times 5, 30. And then, incredibly enough, you just do what we did before, you add diagonals of 2. Now here it gets interesting, watch. 5 plus 8 is 13, correct? So lattice method doesn't get away from carrying, so I put a 3 and a carry of 1. 1 plus 6 is 7, plus 1 is 8, plus 6 is 14. 1 plus 2 is 3, and then 3, and then 1. So you get 1, 3, 3, 4, 3, 2. Can somebody verify that for me? What is 5132 times 26? That number? Sweet. Kick ass. And again, this is not better than our method necessarily. It's got this internal carrying that you gotta do, but it's still nice to know it exists. Alright guys, that's plenty. If you came in after I handed out all the stuff, let me know if you still need your quiz back. Okay. We should have, let me think, real quick. The last quiz we did was last time. I understand that, but we're gonna have another quiz because we're all insane. What do you guys think? Do you want another quiz, or you just? I'm gonna leave it up to you. Some of you guys understand that you want another quiz. Some of you guys haven't done college enough to understand that you want more grades. Okay, so I'm gonna do another quiz, and it's gonna be on what, Jeff? On. See, this last quiz was 3132, right? Yes. So let's do a quiz on 3.3 and 4.1, I think. Let's do that. Well, 4.1 we just did today, didn't we? Oh boy, Jeff. We just finished up 4.1 today. All right. So we'll have a very tiny quiz on section 3.3. A nice, quick little quiz on section 3.3. What's up? Thursday, sorry. Yeah. Did I say tomorrow? I'll do that sometimes. I mean, in the context of the class, the next time I see you.
Is the test gonna be both chapter 3 and chapter 4?
Yes, the test is 3.4 and probably 5.1. So we still have Thursday to do new stuff after the quiz, right? So the test more than likely will not go through 5.2. So you're not gonna have to do 5.2 homework yet. That's gonna be on the next test. It will go through 5.1. I think 5.1 I already did some of it with you guys, so 5.1 will be a nice quick little thing, believe it or not. Okay, that's enough. Okay. I'll see you guys Thursday.